Hello, everyone. Good Monday evening to you. Welcome to another edition of The Physicist and Philosopher. Hello, Dr. Albers. How are you?
I'm very well, thank you, Wayne. And
Good.
how are you?
Doing well, doing absolutely fabulous. Got no complaints because, there's nothing really to complain about.
That's wonderful. It's such a good attitude that you have. It's good.
Well, I figure it's like this. You can look at life two different ways, and now I got everything sized up. You
Uh-huh.
know, I used to be a real asshole. I'll just be
Really?
honest with you. I was a real jerk for many years of my life.
Uh-huh.
I had gotten so off what my life destiny track was supposed to be. And
Mm.
it's like physics is that when you run counter to a opposing force, you're going to get friction, right?
Oh, yes.
Yeah. So I'm just being honest. And,
Mm-hmm.
I think one of the great benefits about having the privilege of getting older is the fact that you have time to reflect. You know what I'm saying?
Yes.
Yeah. All right. So there you go.
That
Now,
that's wonderful. So you changed the
oh,
way you treated other people, basically.
yeah. Yeah. I
And
was,
that changed everything for you. And that's wonderful.
mm-hmm.
Because when you treat others with kindness, you're always telling us to be kind to one another.
Yeah. And
Then
actually,
kindness comes back, doesn't
it
it?
does. It does. I was a CEO and, in the technology sector, particularly if you are a company that's venture backed, you have performance goals that have to be hit.
Mm.
Yeah. And, as I look back at it now, Claudia, to me, it's just, wow, it just sucks the life out of you. It's what it does. So, yeah, I'm a much happier person now. I see things differently, and
Mm.
it's much better. So, welcome everyone. We
Mm.
have almost 39 people in here, Claudia.
Oh, good.
So, lots to deal with. So, welcome everyone. Thank all the moderators tonight. Appreciate it. Thank you
Mm.
very much.
Yes.
So, you see, folks, you do get the balance. You've got today you had the philosopher coming in, and now we will begin to address on the side of the physicist
Mhm.
because that's what everyone's here for.
Yes.
So, you and I were talking
Mhm.
prior to coming on here about the angular momentum of the sun
Yes.
and how when you deal with the theory of a binary star system, that our sun in its size, etc., is too small in the angular momentum.
Yeah. If we go by the theory that the sun formed due to gravitational collapse of a cloud of dust, as it collapsed into that cloud of dust, it should have gained a lot of angular momentum. So an angular momentum is related to how fast an object rotates. So if you think of a skater, you know that they do that
The pirouettes.
the pirouette
Yeah,
where they move their arms inwards, and as they do that, they rotate faster and faster.
correct.
So as the cloud collapses, the sun was supposed to rotate faster, but the sun actually rotates very slowly.
Ours.
So yeah, it
Okay.
takes 24 days to do one rotation. It's extremely slow. So that doesn't make any sense. But I know it doesn't make any sense because I don't think stars form through a collapse of a cloud of dust. They form in another way. But then you were asking about the fact that we might have a binary system.
Mm-hmm.
But to tell you the truth, we actually not only have a binary system, we may have a trinary system, because I know that both Jupiter and Saturn are stars.
That's
And
interesting. Okay.
they emit, both Jupiter and Saturn emit a lot of radiation. They don't emit in the visible range, but they emit a lot more radiation. They're very hot in the interior. I think Jupiter is at a temperature of over 1,200 Kelvin. And, it's out there. So it's not the sun that's warming up Jupiter. It seems to have discharges in its atmosphere. And whenever we have discharges, it's basically the same that's happening on the sun. The discharges cause light to be emitted, electrons leave atoms, you have ionization, and then you have light emission, you have fusion reactions happening, so energy produced. All of this is happening, that's happening in the atmosphere of the sun, is happening in the atmosphere of Jupiter and Saturn. And the other thing they are producing is they are producing capacitor rings around them, which basically is clouds of ions forming rings around the star. Saturn, we know, has rings. That's what these rings are. They rings made out of ions that come from its atmosphere. And we know that because Schumacher-Levy 9, that comet that hit Jupiter, it had only water in its tail until it crossed into the region close to Jupiter. And then its tail became sulfur. There was no water. All the water disappeared, and there was only sulfur in the tail. That's because the ions in a comet's tail come from the environment. And the environment close to Jupiter comes from Jupiter's own rings, and it's rich in sulfur, whilst the sun's outer rings is rich in hydrogen. So it means that Jupiter is actually a star. It even has the same capacitor rings that the sun has. So
it's interesting. Arthur C. Clarke, 2001. That was the premise of his trilogy of his books. They did the movies 2001 and then 2010. Was the fact that some advanced intelligence knew Jupiter was supposed to have been a sun anyway. It had all the construction design, just like you went through, and all it needed was basically, I would think,
ignition.
I was going to say, I'm looking for what's the word? A combustion agent.
Yeah, but the thing is, it's already combusting, but it's combusting according to the electric potential difference between the interior and the outside. So there's nothing actually we can do to make it combust anymore. It has to do with the gravitational potential energy that the star has.
Could it feed off of a stellar core?
No, actually the other way around. The stellar cores feed off the star. And as I said before, Jupiter has gone from having 16 satellites to having, I think, 69. And it's possibly increasing all the time. So it may be that it has gained a lot of captive stellar cores that are draining its energy. And I'm sure Saturn is as well.
Well, we can see Jupiter. It's changing. We know that. Right before our very eyes, we're seeing it. It's getting hotter. We know that. We can see that the dynamics of the wind pattern of the planet has been altered dramatically. Now, I'm 62, and when I look back in my lifetime, I remember as going into elementary school that looking through a telescope, you could see very plainly this red dot that was on Jupiter when it was close in the months of June and July. It's not there anymore.
Don't forget the same thing has happened to the Earth. The Earth has warmed up. The Earth's storm patterns have increased. Basically, the same thing that we see happening on Jupiter is happening on Earth. So,
you're bringing that up because someone had asked, with the changes in the Earth, would we not see an increase in electrostatic discharges in the atmosphere?
Definitely. We should definitely.
And we are we not? I mean, we're seeing sprits now that I don't ever remember seeing sprits.
Yeah, a lot of things have changed in our atmosphere. And as I said before, I recently wrote some articles that I believe that the Earth has at least one stellar core orbiting it. It's
Yes, in
affecting
fact, I'm
us.
pulling that up right now.
Yeah.
So give me a second here. Okay, give me 1 second.
Mm-hmm.
Okay, here we go. There you are. Here we go. Is this the one you're talking about?
Yeah, this is the second one I've written, but it's a good one.
Okay.
And here I cover the fact that rocks, obviously rounded rocks, you can see how rounded they are. You know, it takes hundreds, thousands of years for the ocean to erode rocks until they're rounded like that. So this means that these rocks were at the bottom of the ocean and have been there for possibly thousands of years. Now, suddenly they show up on a road above a beach. And that is just physically impossible for rocks to be moved that have been up there and were submerged. Now, I'm not saying that if this had been rocks from a cliff, a boulder from a cliff, the waves through their pressure can break these rocks and possibly move them a little bit uphill. But these are rocks that were submerged. And pressure from any wave does not work on submerged rocks, because if you try to move water, push water, it just flows over the rocks. So there's no way that waves could have moved rocks that have been at the bottom of the ocean for thousands of years, just move them up here. That's just not, it's physically
it's
impossible.
It's an amazing picture to see this. I know. It's like, what?
Yeah. So what actually had to happen was that the Earth's gravitational field had to be canceled in order for these rocks to be moved off the bottom of the ocean and actually move with the ocean. And the only thing that could have happened is that an object comes overhead, pulls on the rocks, gravitational attraction cancels the Earth. And it shows, I showed as well there that the second picture is these perfectly round. I believe someone said that this is not a sinkhole, but the one on the left is not a sinkhole. But the one on the right is the type of sinkhole that's appearing all over the world. And they're perfectly round.
Yes, they are.
Now, naturally produced sinkholes produced by water or something like that would never be perfectly round. Only a current of particles being pulled up from one of these objects would cause these perfectly round sinkholes. So both the rocks and the sinkholes show that these stellar cores are having gravitational interaction with the Earth and are pulling matter right out of the Earth and causing rocks to float in the ocean. So that's where I started figuring out what gravity is, because obviously the interaction they're having with the Earth is gravitational because they're attracting matter. They're canceling the Earth's gravitational attraction. So then I remembered last year that I saw in stereo images, and you can see some of these stereo images, that the Earth in these stereo images always had a sort of a shadow next to it. And this indicated that there was an object there. Possibly they were hiding part of it, but there was an object there next to the Earth. Sometimes you even see that vertical line that people call Birkeland currents. I don't like calling them that because this is just a visual effect. It's not actually a Birkeland current.
And then we can tell because in Venus, which is a very bright object, if it was due to the brightness, then we should be able to see a similar effect by the camera picking up this dark space. We do not.
That's right. Yeah. So I believe this object, there has to be something there close to the Earth for us to get that type of signature. And then I noticed that over a month, the object was still there. And if you're watching the planets on the stereo, the planets always move apart because their orbits are quite different. If an object stays with the Earth for so long, so this was on March 7th, the previous one was February 28th. And then the next one is later in March. So it's over nearly a month. The object stays right there. So only an object actually connected to the Earth or in orbit around the Earth would stay close to the Earth as the stereo spacecraft moves in its orbit.
I still marvel, Claudia, and I've been studying SETI and I guess now, I don't know, 4 or 5 years.
Mm-hmm.
And it never ceases to amaze me when you see what the camera is seeing and what we're not picking up. Again, our little friend right here.
That's right. It was still there. I think once I started talking about this, they started doing something to the images and it wasn't there anymore. There it is. Again, you can see it almost looks like a shadow. But we can still see that vertical line across the object. Yeah. So on the right-hand side, it's a close-up. But you see it's still there. This was on March 25th. And I think I went back. I don't have the images anymore, but I went back into October of 2016, and this thing was still there. I was already there. And it stayed there for months until I think they started doing something to the images. And then it didn't show up anymore. But I actually found out that what they do is when something appears that maybe indicate that there's an object that we're not supposed to see, then they keep on adding that particular thing to all the images so that we start thinking that it's to do with a camera, to do with a detector. They often do this. I actually caught them doing this with the Core 2 images, where they have these images before they process them, where they look very rough. And there's this little darkness below the sun, wasn't there in the unprocessed image. And then they processed it and they added it.
And they do. Listen, I've got rare footage from, get this, I had it from Stereo B. The Stereo B is no longer operating. They say it's fried. I don't think so. I think what my theory is that Stereo B was showing way too much. In fact, I'm convinced of this, Claudia. When Stereo B went down, the images that it was giving us was of a solar system that was not what was being taught in schools.
Yes.
And then mysteriously, Stereo B goes down. My foot. Anyway, I digress.
Yeah, because everything is different from what we've been taught in school. That's what I discovered. That's why I figured out gravity is a lot like electricity, like the electric interaction. It has two poles. The electric interaction has positive charges and negative charges. Well, so does gravity. There's repulsion and attraction in it.
Now, you see, I happen to agree with that. You and I have exchanged ideas. Now, I just want to get on something before we move on, Claudia. So what we're seeing here are photons. These are high energy particles coming off of the sun, right? And it's here we can see, and the thing that people don't understand is that we have spatial distortion. So we got a camera that's looking out. It has a number of other cameras on it. But what I always find is interesting is that when I begin to see the interaction of fields right here, and especially right here. So the darker, and am I right or wrong on this, Claudia, is that when we see the darker the image, is that darker mass or is it darker density that the photons are being obstructed by not being able to go through?
In this case, basically, it's a question of contrast, really.
Okay.
And plus these images are doctored like crazy. You see that blue on the left image, that blue region there. I think they actually doctored that to look blue like that, to cover up something that was there.
Well, I don't understand how photons move in a straight line here.
Exactly. I don't think so either. I think there's a lot going on in these images that they don't want us to see.
Do you see the thing that I have now? I know what the detractors say. But I've been looking at these for years, folks, so I can see something. What I don't think people are catching is this huge object right here.
Exactly.
It is freaking, and here's what people are not seeing, and we're going to reveal it right here tonight.
Mm-hmm.
You can see how the photons are interacting with this object. And this object is huge.
It is huge. I've been catching these objects for a long time. Don't forget, in these images, these are stereo images. Do you know how small the sun is in stereo images?
Yes, ma'am.
We know from the core 2 images. So the sun would be off to the left. It will be the same size as that little circle on the core 2 images. That's how small the sun is.
And this, folks.
That is huge.
Huge.
Absolutely huge. But they've somehow doctored the image so that it looks almost like a transparent circle. But when you look at it right, you can see the edge. There's discontinuity at the edge. So this is a solid object.
You know, Claudia, this just hit me as I was looking at this. Remember the NASA footage I showed you where we saw the beam coming into that object? And what people did not see, if you actually speed those frames up, you see whatever this thing was, it was rotating. Look at this. It has this, and I'm not saying that it is the same, but it has a similar signature here where we're getting, what would be the right term for this? Is that an obfuscation of light?
You know, I don't know. I know the object is there because of its
I can see
outline.
it right here. I can see it right here.
What they've done, they've doctored the image so much. It could be that what we're seeing at the top is actually the sun, a solar jet interacting with the object itself. I am not sure. It's hard to say exactly what they've added to the image and what is a real effect in this case. But one thing we know for sure, there's a huge object there.
It is, and I have caught it myself. It's so okay. So where we want to go to next?
Yeah, well, this is the stellar core.
Yeah,
or at least one of them, or at least there's one that has been captured by the Earth. So as you can see, it's a solid object surrounded by a cloud. Both the object and the cloud are emitting light. And it's red light in this case. I think it changes depending on whatever particles it's getting from the Earth. There's also a straight line. You can see that straight line. That straight line is also a particle current, probably electrons going from the Earth's outer layer towards the cloud of the object. But the cloud is like a coma of a comet because it's pulling matter from the Earth, and this matter is going out and surrounding the object. And then we see those little dots around it. And a lot of people think those are stars. Those are not stars. This is actually debris.
Here?
Yes, it's everywhere. If you look at any satellite image of the sun, any spacecraft image, you will see these clumps of matter. They are debris. These old stars shed their outer layers and in clumps like this. And some of them can be quite huge, moon-sized. Some are smaller. This one is obvious. These are smaller. But if you see the sun having CMEs in the cactus images, you can actually see all these particles moving as if buffeted by the wind.
Mm-hmm.
So these are not stars. These are particles brought in by these objects into the solar system and the corona, the outer corona. Even now, outside the Earth's atmosphere is full of it because it comes from them.
And the thing where my mind, when I see this is that I look at the equation, and the equation that I see in here is the fact that how can we know what we do not know? And I love how you said, because, if you take by the first and second law of thermodynamics, that energy is neither created nor destroyed, but is in a constant state of process of change, then that means energy would have different dynamics even beyond our understanding of physics. correct?
Yeah.
Or am I wrong on this?
No, that's correct. Now, the largest violation of conservation of energy is the Big Bang Theory.
Mm-hmm.
But
You're right. That's absolutely right.
creation of matter is happening everywhere in the universe. Halton Arp, the astronomer, proved it through his study of quasars and how they are connected to low redshift galaxies. And he came up with the idea that redshift is intrinsic, not due to recessional velocity. So,
could I just ask, I feel like the student here, so I'm going to raise my hand.
okay.
So people would have a potential problem with the statement you just stated in the fact of energy, right? Mm-hmm. Being brought in, created constantly. But I would challenge anyone who would challenge that. And here as a student, I would ask you is that I'm drawn back to the quantum level, that if quarks can come in and out of our dimension of reality, is that not a transference of energy?
Yeah, that's right. So you see, in quantum mechanics, we have what's called zero-point energy, which means that space itself is at a higher energy than zero. So there's an infinite amount of energy in space itself. And I reached the conclusion that particles are resonances or fluctuations in space, like a node.
Okay.
So particles are made out of space energy.
I can see that.
So it means that matter can just be created out of that energy because that energy is there and there's an infinite amount. And
Claudia, what I see as well, people don't understand plasma. They don't understand the fourth state of matter, do they?
Mm-hmm.
You know, I can remember when I lived in Austin, Texas, twice I saw the space shuttle come over as it was landing in Florida. And in both times, the most spectacular thing about that I remember it landing was the plasma trail that it had directly behind the wings, and how literally 30 minutes after it had passed over, the plasma was still going through a state of cooling. So when I think of plasma, and then I begin to think about what you are teaching us here and how energy can actually, as you said, could be shed into another form, makes perfect sense to me. If we all, with plasma being into that equation, I guess is my thought here.
Yeah. Oh, okay. You want me to explain what plasma is?
Yes, please.
Okay. So plasma is actually particles. It's particles that are charged. So we have the electron, which is on the outside of atoms, and we have nuclei, because atoms have protons that are positively charged in the nucleus, and they have electrons outside. And in a neutral atom, you have the same number of protons as electrons. So you have zero charge. But when the atom loses an electron, it becomes positively charged because it has one proton too many. So it has a plus E charge. So it becomes, it's what we call an ion.
There we go.
So then we have the two separated from each other. So if we have a potential difference across, what happens is the ions flow in one direction and the electrons flow in the other direction, opposite each other. And that causes a current to flow inside this material. And when a material is mainly made up of these ions and electrons, that's what we call a plasma. Now, they don't react chemically because ions of different elements will repel each other. They're both positive. And the electrons will repel each other as well, according to the electrostatic interaction. But sometimes one of the atoms will capture an electron. And when it captures the electron, and as the electron moves down to its lowest state, a photon is emitted, because photon is energy. But photon is also light. So we have light being given off by the plasma because of this interaction. That's basically what happens.
I love it. That's what it is. Okay.
So, yeah, these are the Van Allen belts. The Earth has Van Allen belts, and the inner zone is the proton belt, and the outer one is the electron. As you can see, that the structure is always the same in the universe. The inner is positive, the outer is negative. The Earth does have another electron layer, which I believe is above the ionosphere. This layer is made out of particles that are coming in from the sun. They're not actually Earth particles. Earth's own particle. Earth has a core which is very dense in protons because it's made out of heavy nuclei that have a lot of protons in the nucleus. And the gravitational interaction causes a lot of the electrons in these atoms to be pushed outwards to the outer layer of the Earth, so that the inner core of the Earth is positively charged and the outer layer is negatively charged. This is how all objects in the universe are, and this is due to the gravitational interaction. And then there's an electric potential between the inner and the outside, and that's what stars use to produce light. But even a planet has that because of the gravitational interaction that causes all objects to do this, to have an outer layer of electrons. And so all planets, all stars are super atoms. The structure we see in the atom is the structure we see in planets, stars, galaxies, and everywhere else. We always have the inner is positive, made out of protons mainly. The outer is negative.
If gravity is present, would it generate heat? As I'm sitting here listening, as we would have opposing forces coming in here, because gravity is a force, would it produce friction or heat?
The electrostatic interaction will cause the heat. The gravitational interaction, all it does is it causes protons to be very strongly attracted to each other. So it causes the strong force in the nucleus that attracts protons to protons. And that same force is what causes large objects to attract to each other. So basically, the strong force is the gravitational interaction. But there is another one, and that is the fact that protons and electrons repel each other.
Right.
Which is opposite to the electrostatic, because in the electrostatic, protons and electrons attract each other. But in the gravitational, they repel each other. And if the gravitational didn't do that, every atom would collapse. We wouldn't have atoms. We wouldn't have life. It's the gravitational interaction that separates the proton and the electron so that atoms form, so that stars form, so that galaxies form.
Yeah, you would have even on the subatomic particle. Yeah, okay. All right. See, folks, you are learning. I told you this was class.
That's good. So this is one of the stellar cores in the sun's corona, because then I said, well, we have objects that are absorbing energy from the Earth. Just like these ones are absorbing energy from the sun. And they seem to hover in the same position with respect to the sun for quite a few hours sometimes. So they possibly are doing the same to the Earth. So they have a kind of an erratic orbit where they may be out there for a while, possibly further than the moon. And then when they are able to, they come in, because I think they repelled initially, and they may have done this with the sun as well. They spiral in slowly, and as the energy increases, they're able to come in further, closer and closer to the sun, and closer to the Earth. Then they come in, they draw a current of protons. Actually, basically neutral. They can be neutral matter, and the current of electrons, like comets do. But it's not quite the same. They actually look for very dense a matter as they can reach. That's why we then get the sinkholes. They're pulling matter right out of the surface of the Earth and some distance into the surface of the Earth.
I would call that in my writing that's a gravity well, sucking it right up.
Basically, it is, because I figured out that these stars are actually neutron stars, because when the gravitational interaction is not strong enough, the proton and the electron unite and form neutrons. And these stars have used up just about all of their gravitational energy. They dead stars, basically. So on the outer layer, the protons and the electrons have combined to form neutrons. So they basically their surface is neutrons. But as they collect matter from the Earth or from the sun, they start getting a layer above that of protons. And then these protons will draw more protons from the Earth. So that's how they draw matter from the Earth.
Okay.
And here, so here we see, I think it's what these particles, as you can see, it's got a tail like you'd expect a comet to have. And the tail would be some of the material that it's drawing, maybe drawing from the atmosphere sometimes. And then it has a type of a coma, just like comets, because they're drawing the same sort of material that a comet would draw. But a comet can melt once it gets large enough, self-gravitates into a spherical object where all the matter, the densest matter, goes to the center. These objects are very old. They cannot do that. So all they can do is gain matter on the outside. And then wherever that matter is dense enough, it connects to something on the Earth and pulls more matter towards that matter. That's why it's making these cylindrical type of connections with the Earth. I believe that's what it is. I need to think about it some more, but I think that's what they are doing. So this is the sun. This is the solar capacitor. This is how planets form. They form in the solar capacitor. And these rings are rings of gravitational potential that decreases as we move outwards. And the comet comes in with a potential that's lower than any of these rings. And it also plays with the electrostatic potential, because the sun the corona is negatively charged, so there's a negative electric potential there. And then there's a positive potential on the other outer layer. So we have electric potential and gravitational potential. Now the comet is at the different potentials, so it draws current. It draws electrons from the corona, so that's the blue circle around the sun. And it draws positive ions from the ion ring or the sun's nebula ion cloud behind it. And that forms the tail. Then the electrons and the ions interact at the comet itself, and that forms a coma. Around it, it starts producing light. It forms water because hydrogen and oxygen combine to form water. Once the electron has been captured by the hydrogen and captured by the oxygen. So then they react, that creates heat as well. Some of the electrons move right into, that orange triangle there at the top? That's the tail of the comet. So some of the electrons move right up into that tail. They interact with the ions, and then the tail starts emitting light from that interaction. So that's how comets form tails and comas. The coma, it starts gathering material and it gets larger by gathering more material. And also its orbit becomes more circular every time it comes through the inner solar system. So that's why comets eventually turn into planets. This is how stars capture planets and how planets form.
When I see this, I wonder sometimes if we've yet to discover a material or a substance that would actually be the antithesis of what light would be. In other words, it's an object that would basically consume the photons, the energy of an object such as a sun, but yet the object itself would be virtually invisible to our light spectrum.
Well, we actually have that because the
Oh, we
stellar.
did? Okay. All right. I didn't. Yeah. I mean,
Okay.
that's what I'm getting when I'm looking at this. I mean,
What we have there at the center is a stellar core. When they come into the solar system, they don't emit visible light. They may just be hot enough to emit some infrared.
mm-hmm.
But they cool. They dead stars. They do not emit light. They hardly emit any radiation at all. But they are still made out of protons. But these protons have lost most of their gravitational potential, which comes from the photon that the matter came from. Because I found out photons are actually made of two particles. They split, and the two particles come out. The two particles are the proton and the electron. That's how matter creation is occurring. It's coming out of photons.
Would these
coming out of light.
Have a dense magnetic field as a result?
Not really. Don't forget, the magnetic field always works with the electric field. Whenever we have charges that are moving, we have a magnetic field. So I don't actually consider magnetic fields. I rather go into the electric field itself, which is the source of the magnetic field. And it's the electric field that works with gravity, because it's when a photon moves through a region of electric field, it's the electric field that causes it to split into its constituent particles. So the proton is pulled one way and the electrons pulled the other way.
If you had a sun, though, that would act like, let's say, as an electromagnet, that you basically would have this object, the stellar core, coming in, which would generate a positive connection to our sun. What I'm trying to think of would be like adding electrical current to it.
This is actually what happens, because the stellar core comes with a much lower gravitational energy than the sun. It has basically lost most of it. So it comes up to the sun and starts drawing current from the sun, just like comets do.
Mm-hmm.
But
wow. Okay, I'm seeing that. I'm sorry, Dr. Albers, it just connected to me that I think one of the dynamics that we don't understand about comets that we're now beginning to understand is all of a sudden I'm seeing is this electrical current that's being generated.
That's right. So they actually, stellar cores are like super ions. They've lost most of the electrons. Most of them have combined with protons, so they have a neutron outer layer. The electrons are weakly attracted to each other, so they're easy to lose. So over time, a star loses electrons to the galaxy. So these are like super ions. They like positive. And so they don't have enough electrons. So what happens is when they make connection with the sun's corona, the first thing that happens is they draw a huge current of electrons from the sun.
I see that now.
When that happens, the sun's driving potential drops way down. What happens? The sun goes dark.
Holy crap. Okay. All right. And I think that's why we see on SDO I think that's why we're seeing the increase of these, what they call these corona holes.
Yeah, not just the corona. The coronal holes are a little bit different. The sun going dark means the electrostatic interactions, the lightning happening in its atmosphere just stops because the potential dropped way down, the potential difference.
I have a question for you. Would the human eye be able to pick up if the sun was really, let's say, going through fluctuations? We wouldn't be able to see that light fluctuation with the natural eye, would we? I doubt if our instruments would.
Well, the thing is, this is the first thing I picked up about the sun, was that in the SDO images during the so-called SDO eclipse, the sun was actually going dark. That's why the trolls fought against that so much. But they left out one little detail. The corona shrinks back that is irrefutable evidence that the sun goes dark. Because if I think it's in my previous article, I don't know, I think it was on 160. I actually show the images.
I have 180, so I'll need to go back and look at it. Okay.
I actually show the image that if the Earth had been covering the sun and it was causing the bottom part to be dark, then the corona would be covered at the same time. But we actually see is the top regions, the corona shrinks back like this. And so there's a little region here.
Which one would you like me to pull this up in?
Yeah, so there's always a region where a little triangle at the edge where the corona should be there, and it's not. It's not there because it's shrinking back as the sun goes dark. And I always thought, yeah, the sun is actually going dark, but everybody fought against that until I found the fact that the corona is shrinking back.
Look at this. You know, this is what amazes me at the poles, and it doesn't matter what you know, let's see, we can go, well, let's go up in here into the, look at this.
Yeah, we can see the corona is shrinking horribly. And the largest effect, I think Scott was showing me, we had a live stream this morning, was between 2015 and 2016. The sun went dark. The same thing happened with ice on the Earth. The North Pole lost the most ice between 2015 and 2016. And what causes these coronal holes is wherever we have a coronal hole is we have low density of coronal particles. In other words, low pressure. What's happening to the Earth? Why do we have so many severe storms? Because of intense low pressures. Because these objects are just pulling particles off the sun's corona and off the Earth's atmosphere. It's the same mechanism.
Can I ask a question here as I'm looking at this? So I'm trying to think from a physical law perspective, Claudia. Why is it now that at the poles, they're no longer anymore, it doesn't seem to have any reaction going on here? There's permanently...
They're permanent coronal holes.
Yeah, permanently.
I know. And this is because of the sun's weakness and the fact that it's losing its corona. And the sun's corona is its outer layer of electrons. So the sun is losing its outer layer of electrons. This is why it's getting darker and darker and darker. And this is because of the interaction of the stellar cores. This is how we can see that the sun is being drained. And if you compare the sun now with what it was in 2011, I've done this comparison in many articles. Mm-hmm. And comparing times when we were about the same time away from the last solar maximum or the last solar minimum, you can see a huge difference in the sun. The sun is so weak right now.
You know, I don't think people are realizing it. And, you know, what I see on this, I just get this... I'm dating myself, but Lost in Space, you know, I'm hearing the robot going, "Danger, Will Robinson." You know, it's like, this is not good for all life forms.
No, it's not.
It's not. I mean, I'm seeing, look at this. I mean, folks, Claudia, what I see in this visible light spread, and I think that when they're 197 angstroms, I think, nothing. I mean, this is like looking into the pit of the beast. Mm-hmm. I mean,
that's right.
It's the pit. It's the abyss.
Mm-hmm.
I mean, I don't. That's what I get from this, and this is it's disturbing.
It is disturbing, and but the thing is, when I started looking at this, and I knew there were stellar cores there interacting with the sun and draining, I could clearly see that this was happening. The most surprising thing for me was to discover that these objects are around the Earth as well and doing the same sort of thing to the Earth, you know, causing huge changes.
I never even thought about that. Wow. Hadn't thought about that.
Yeah, because what they do is they come into the solar system And they're so drained of energy, they just attach themselves to anything they go by first, it seems.
Sure they would be. Yeah, that would make sense.
So that's why Jupiter has captured so many from 16 to 69. So this is what the whole solar system is affected. It's not just the sun, it seems. And to me, this was a revelation, because I thought in the beginning they were all going to the sun. But the evidence was there from the beginning, because it seems that magenta colored light is actually very likely coming from these objects that are close to the Earth, and not from the ones that are close to the sun.
Mm-hmm.
And this magenta light, and you saw that one was emitting red light. It seems that emits different light at different times,
yep.
possibly depending on what material it's gathering from the Earth.
I'll tell you what, Claudia, we're seeing some very, very strange stuff in our atmosphere, are we not?
Mm-hmm. Very, very strange.
So I guess the question becomes, where is this leading to? Where are we going now? I mean,
you see, this is very difficult thing to say, because basically things have been getting worse for many years now, and they're not likely to get better. They will continue to progress. Our magnetic poles are shifting because we having crustal displacements, small incremental ones, not huge ones, small ones.
Mm-hmm.
And this will continue, and they possibly will increase as this object, or perhaps more of them, gain more energy. They may be able to come in closer and closer to the Earth. Earthquakes, volcanic eruptions, the weather.
So, one of the areas that I think that we're seeing what you're talking about specifically is here in Papua New Guinea. Mm-hmm. Something is going on, Claudia, in this. Anyone can do this. We won't do the work for them, but you can just go back and you look the last 3 weeks in this region. I saw helicopter view from their government. Mm-hmm. And Claudia, the land is being transformed. It's something is seriously going on under this region of our planet.
Yeah. And these objects will be attracted to places where there's a higher density of matter. The attraction is, like Scott likes to say, is almost like two magnets attracting. They attracted to areas of high density of matter, as if there was a large magnetic field there, and it's attracted to that. So it could be that there's a region here where there's dense matter that's not too far from the surface of the Earth or from the bottom of the ocean, and these objects keep getting attracted to this region.
Is that why we would see certain areas having more activity than other? Yeah, okay.
Mm-hmm. Yeah, I think so. And also, I think they are attracted to the North Pole, possibly because it's ocean there. And, whenever you have an ocean, the denser part inside the Earth is closer to the surface of the ocean, because the crust is thinner there. So and also at the poles, the magnetic field lines go into the Earth, and that's where it may be able to reach in closer as well. So maybe why it's attracted to the North Pole and maybe causing these changes, actually just pulling atmosphere out.
Yeah.
And causing a huge low pressure, which will then cause possibly cloud formation, heat to increase under that, and then it could split the vortexes over the North Pole. And I think it has something to do with this, with what these objects are doing. And now I understand it's a gravitational attraction that they have for matter on the earth, the atmosphere, the ocean. They suck the ocean right up. It piles up in one region, and then it will cause an extreme low tide somewhere else. So this is where the water recession is coming from as well.
And I'm just pulling this up on the, this is Null School. This is at, I believe it's 70,000 feet. We still have the northern polar vortex, which is, a little hanging around. So we're seeing these changes, just as you said. I'll give it a...
Definitely the climate is not normal. We have extremely large vortexes, and this will go along with the fact that we are getting extreme low pressures. And extreme low pressures will cause extreme storms.
Well, in fact, you folks in the Northeast, well, you're on the Northeast. Let's see and I think we can actually describe what you're talking about specifically. So here's the thing, folks, here, just to give you an idea. This is what we're seeing right now. And look at this, Claudia. There is this huge high ridge system. When this thing breaks down, and this is where you're going to get that nor'easter this weekend. Everything you've been saying is, in fact, happening.
That's right.
Well,
we understand what it is. Unfortunately, the news is not good. It's not likely to get better anytime soon. But people, I think it's better to understand and know what is going on than not knowing.
I think that, listen, that's the whole balance we do here. And that's why we call it the physicist and the philosopher. Because, listen, we've endured these changes as a species before. Humankind has the most resiliency to adapt to its environment. The earth changes all the time, Claudia. It's just, people get wrapped around the axle about global warming. And I say, well, just settle down a little bit. This is what we have when we have climate change. And this is what our planet does. And so I agree with you. And what I really appreciate you so much sharing with, there's 366 people in here tonight, is the fact that we're presenting the point of view of both science, we give philosophy, and we'll give religious views as well. It all plays into what we are.
Yes.
And you are a great teacher.
Thank you.
I just want to tell you that.
Thank you. I
appreciate you so much. And everyone else is here as well. You attract a crowd.
That's wonderful. Yeah, I enjoy teaching. I enjoy imparting understanding to others. I enjoy understanding the universe. This is why I became a physicist. But I enjoy imparting that understanding to other people. I think it's wonderful to understand the world you live in. And it should uplift you. It should make you happier because you understand why things in the world work the way they do. And it's a huge, instead of watching TV, which is just meant to dumb you down, you can actually understand how the universe works.
Gee, what a concept.
And then you have these ideas in your mind that you can think about. Yes. Because physics takes thinking. Sometimes the concepts are difficult to understand. You have to think about them over and over again.
You do. I mean, and I'm the type of guy, I like to compartmentalize. If I have a really big problem, I learned years ago, you can't attack a big problem. You're going to end up failing more than you'll ever succeed. And then you get discouraged and you give up. What I've often found is that if I don't understand something, I find something that I do. And that's what I love about what I learned from you is that I may not understand the complexity of the math itself, the calculus, everything else that goes into it. But if I can begin to understand the principles, then I can begin to understand the equation.
That's right. And that's very good. And I remember that's the secret to programming. You break down the problem into little bits. I even remember that because I did programming in my first few years at university.
8, 16.
Just a little bit.
And
that was the secret.
That was the secret. Listen, when I was CEO of a software company down in Austin, Texas, actually had our office right down on 6th Street. But that was the marvelous thing, was studying, back in those days, we were looking at Cobalt as a data system. And, the complexity of the systems always seemed to be so complex on the surface. But when you really get back down to it, it's just a matter of how they're arranging the data flow. In essence, That's
right. You can break every program down into the little iterations it goes through at every step.
By the way, if y'all don't know this is how hackers work.
Well,
maybe I shouldn't have said that, but that's how hackers, that's how they operate. So, well, Claudia, it's been another fabulous hour.
Yeah. Wow. An hour has gone by already.
It's gone by. And we have just a packed room in here tonight. Listen, everyone, Claudia and I just thank you so much. You have a lot of choices you can go to, and we just appreciate you come here. And Claudia, I just want to say thank you as a student.
Well, thank you.
A teacher.
Thank you very much, because as you say, I'm a teacher, so I enjoy teaching. So I enjoy the opportunity.
Well, apparently you have a lot of students here.
Wonderful.
I have to say, listen, I look at this as that you have basically a classroom that has over 375 students.
Wow. That's wonderful.
Yeah, tell your colleagues that.
Yes.
All right. Have a great week, Claudia. We'll see you next Monday.
Thank you, Wayne. You too.
Okay, everyone, be good to yourselves. We'll see y'all real soon. All right. Good night, y'all.
Good night.